In July 2022, the team at the Space Telescope Science Institute in Baltimore sat there, watching as their screens suddenly went quiet. The first infrared frames from Webb had just arrived, and Jupiter was glowing in ways the physics didn't predict. Features appeared in bands where atmospheric models promised uniform flow, and bright patches flickered at wavelengths that should have shown darkness. This wasn't a distant exoplanet or a galaxy at the edge of time. This was Jupiter, a world we'd mapped with Voyager, Galileo, Juno, and 4 centuries of ground telescopes. We knew its rotation period down to the second, its wind speeds to within meters per second, the chemical signature of every cloud deck. But the Webb images showed structures that had no place in the atmospheric circulation models. Thermal emissions spiked in regions that should have radiated evenly, and in one narrow longitude, between the equatorial jet and the North Tropical Belt, something was moving at 180 meters per second faster than the surrounding flow. The lead scientist flagged the coordinate and asked the imaging team to recheck the calibration. The calibration was correct. What nobody knew at the time was that the strangest thing in those images wasn't a storm or a light show, but something moving where the old map said nothing could move. The giant. Jupiter holds 318 times the mass of Earth inside a volume so vast you could fit every other planet in the solar system within its diameter with room left over. Its great red spot alone is 16,000 kilometers wide, large enough to swallow our world twice. For 400 years, since Galileo turned his refractor toward it in 1610, we've catalogued its moons, timed its storms, measured the drift of its cloud bands. By the time Juno entered orbit in 2016, we'd built atmospheric models that predicted temperature, pressure, and wind velocity at every altitude. The textbooks showed a planet of orderly zones and belts, jet streams locked in place by the Coriolis effect, storms that raged for centuries but never surprised us. Jupiter was predictable, a solved problem in planetary science. Missions had traced its magnetic field to 20,000 times Earth's strength, counted lightning strikes in the polar vortices, mapped ammonia concentrations down to parts per million. The remaining mysteries were details, refinements to models that already worked. We thought the surprises were behind us. But the eye we'd been using to watch Jupiter for 400 years was about to be replaced by one that saw an entirely different planet. The new eye. The James Webb Space Telescope doesn't see light the way our eyes do. Its 6.5-meter mirror collects infrared radiation, wavelengths too long for human vision but perfect for piercing dust, reading heat signatures, and watching molecules glow. Where Hubble showed us Jupiter's ammonia clouds lit by reflected sunlight, Webb would see thermal emission from 100 kilometers deeper, where the atmosphere radiates its own heat into space. Webb launched on Christmas Day 2021 and parked itself 1.5 million kilometers from Earth at the second Lagrange point, where its sunshield keeps the optics at 40K. Cold enough that the telescope itself won't drown out the faint infrared whispers from distant galaxies, or, as it turned out, from weather systems on a planet 600 million kilometers away. Planetary scientists requested 2 hours of Jupiter observation time during Webb's commissioning phase, partly as a calibration target, partly to test whether the telescope could track a fast-moving object so close to home. Nobody expected science results. The Juno orbiter was already there. Hubble still watched the storms every year, and Jupiter's infrared spectrum had been mapped by ground telescopes since the 1960s. But the request was approved, and on July 27, 2022, Webb's NIRCam instrument locked onto Jupiter and began a scan from pole to pole. Because in infrared, Jupiter would not look like the striped marble in our school books at all. Infrared sight. Infrared doesn't see cloud tops. It sees heat bleeding through them. The deeper the warmth, the brighter the glow, which means you're looking at atmospheric layers kilometers below what visible light can reach. Jupiter radiates nearly twice the energy it receives from the Sun. Leftover heat from its formation 4.6 billion years ago still leaking out. That makes it a furnace wrapped in gas, and infrared cuts straight through the wrapper to map where that furnace runs hottest. Ground telescopes had glimpsed this before, but their resolution was measured in thousands of kilometers. Webb's optics resolve features down to 200 kilometers across, sharp enough to see individual storm cells and atmospheric waves no instrument had ever isolated. The team knew they'd capture structure. They didn't expect the structure to be waiting in places Jupiter wasn't supposed to have it. So when the first true frames came down, the room reacted before anyone could say what they were looking at. The first frames. The data arrived at the Space Telescope Science Institute in Baltimore at 11:47 a.m. Eastern. Raw sensor counts, noise still embedded, waiting for calibration pipelines to convert photons into something human eyes could pass. By early afternoon, the first processed composite was on screen, and the lead imaging scientist later told reporters the silence lasted longer than usual. Jupiter filled the frame, pole to pole, glowing white and orange against black space, its moons pinned like sparks beside it. But the brightness distribution was lopsided. Certain latitudes blazed hotter than models predicted, while others sat dark where convection should have been churning heat upward. The banded structure everyone expected looked fractured, segmented, interrupted by cold patches that had no clear explanation. They ran the calibration again. The asymmetry held. The more they enhanced the picture, the more one region refused to behave the way physics said it should. Something wrong. The first anomaly sat at 22 degrees north latitude, a streak of infrared emission 4,200 kilometers long, glowing 18K hotter than the surrounding belt. No storm sat beneath it in visible light. No convective plume had been logged there by Juno's microwave sounder 3 weeks earlier. Then they found the gaps. Dark voids where Webb's 3.23 micron filter recorded almost nothing, as if the atmosphere had gone transparent or the heat had been siphoned away. These weren't shadows, they sat on the daylit hemisphere. They weren't polar, they straddled the equatorial zone where Jupiter's fastest winds churn constantly. By the second day, 11 distinct features had been flagged for follow-up. Some pulsed in brightness over the 10-hour rotation. Others held steady, but shifted longitude faster than the wind speeds allowed. One sat directly above a white oval that Hubble had been tracking since 2019, but its infrared signature didn't match the oval's known depth or temperature. The imaging team drafted an internal memo requesting an emergency theory working group. To understand why that mattered, we first have to look at the one feature everyone thought they already understood. The Great Red Spot. The Great Red Spot is a hurricane 3 times wider than Earth that's been raging since at least 1831, possibly since 1665. Ground telescopes see it as a brick-red swirl against Jupiter's pale southern hemisphere. Every infrared instrument before Webb saw it as a cold, dark void, because the storm's towering clouds block heat rising from below. Webb's NARCam saw it glowing brilliant white. The storm wasn't cold. It was radiating at 1350 Kelvin in the 2.12 micron channel, hotter than the surrounding cloud deck by 140 degrees. The temperature inversion meant something inside the Great Red Spot was generating its own heat, or trapping energy the way no other Jovian storm does. The imaging team ran the calibration sequence 4 times. The glow was real. A storm that should appear as an infrared hole was instead the brightest thermal feature in Jupiter's southern tropics, and no atmospheric model predicted that flip. But this legendary storm had been quietly vanishing for a century, and Webb caught it mid-disappearance. A shrinking storm. In 1879, the Great Red Spot stretched 41,000 kilometers east to west. By 1979, Voyager measured it at 23,000 kilometers. Hubble's 2014 observations showed 16,500 kilometers. Webb's July 2022 frames captured it at 15,800 kilometers, and the storm's perimeter had shifted from an oval to something closer to a rounded trapezoid. The shrinkage isn't uniform. The storm is losing width faster than height, compressing vertically, as if something is squeezing it from the sides. Wind speeds at the edge have climbed from 430 kilometers per hour in the 1990s to over 650 kilometers per hour today. The tighter the vortex gets, the faster it spins, but that acceleration is bleeding energy somewhere. If the trend holds, the Great Red Spot could collapse entirely by 2150, or stabilize at a new equilibrium no one can predict. What Webb's thermal map revealed is that the storm's core is now hotter than its edges, the opposite of what Galileo and Juno measured in visible and radio wavelengths. Yet the storm's fading was only visible because Webb's colors were telling a story the human eye could never read. The colors lie. Webb doesn't see color the way we do. Its cameras capture infrared light between 0.6 and 28 microns, wavelengths human eyes can't detect. Engineers assign visible hues to each filter after the fact. Blue might represent 2.12 micron emissions from high-altitude hazes. Orange could map 4.44 micron methane absorption in the mid-troposphere. White marks the hottest thermal peaks. The palette isn't arbitrary. Each color is locked to a specific altitude, temperature, or chemical fingerprint. A patch that glows cyan in one filter and red in another tells you the cloud sits 80 kilometers higher and 60 degrees cooler than its surroundings. The Great Red Spot's white core means Webb was seeing through 200 kilometers of ammonia ice to a warm convective engine below. False color turns invisible structure into visible geography. What looks like Jupiter's smooth butterscotch surface in Hubble photos becomes a topographic relief map in Webb's hands, with peaks and valleys separated by pressure and heat instead of rock. The technique is older than space telescopes, but Webb's sensitivity is 100 times sharper than anything that came before. Once you know how to read those colors, Jupiter's calm bands turn out to be anything but calm. Bands and belts. Jupiter's stripes aren't paint. They're rivers of ammonia ice crystals flowing east and west at speeds up to 335 miles per hour, stacked in altitude like traffic lanes on a vertical highway. The pale zones rise high and cold, where ammonia condenses into white clouds. The darker belts sink lower, exposing warmer reds and browns from phosphorus and sulfur compounds baked by ultraviolet light. The boundary between a zone and a belt is a shear layer, where winds moving in opposite directions grind past each other with the energy of a continental jet stream. That grinding spawns eddies, some the size of Earth, that peel off and drift through the bands like logs in a river. Hubble caught the biggest ones. Voyager saw a few dozen. Webb's infrared eyes counted thousands. Each band sits at a slightly different temperature and pressure, which means Webb's filters can isolate them layer by layer. A zone that looks solid white in visible light splits into 3 or 4 subbands in the infrared, each with its own wind speed and chemical signature. The atmosphere isn't a set of neat stripes, it's a vertical stack of weather systems, each unaware of the others, all sliding past each other at different speeds. Between those neat stripes, Webb found a churning skin of chaos no previous telescope had resolved. The turbulent skin. Zoom into the gap between 2 bands and the image explodes. Plumes of ammonia ice punch upward from the warm belt below, rising 30 or 40 kilometers before they freeze and collapse back down. Vortices the size of Texas spin in the shear zones, sucking in surrounding cloud and spitting out filaments of gas that stretch for thousands of kilometers. Some of these storms last hours. Others have been spinning for decades, unnoticed until Webb's resolution pulled them out of the noise. The surprise wasn't that Jupiter has weather. It's that the weather operates on so many scales at once. A storm 500 kilometers wide sits inside a jet stream 10,000 kilometers wide, which itself is embedded in a band that circles the entire planet. Each scale feeds the next. The small vortices merge into larger ones. The larger ones pump energy into the jet streams. The jet streams carve out the bands. It's a cascade, and Webb caught it mid-flow. What drives it all is heat rising from Jupiter's interior, but the details get messy fast. The energy doesn't rise evenly. It comes up in bursts, concentrated in the belts, which is why they're warmer and darker than the zones. Those bursts trigger convection cells that churn the atmosphere like water boiling on a stove, except the pot is 90,000 kilometers wide and the liquid is metallic hydrogen. All that motion, though, was nothing next to the light erupting from the planet's poles. Glowing poles. Webb pointed at Jupiter's north pole and saw a crown of fire. The auroras stretched 1,000 kilometers above the cloud tops, glowing in infrared wavelengths that trace ionized hydrogen, a signature of particles slamming into the atmosphere at 1,000 kilometers per second. Earth's auroras release about 100 gigawatts during a strong storm. Jupiter's dump 1,000 times that, continuously, every hour of every day. The energy flux is so high that if you could harvest it, you'd power human civilization for a year in 90 minutes. The mechanism is the same as on Earth, but scaled to nightmare proportions. Jupiter's magnetic field stretches 3 million kilometers into space, farther than the distance from Earth to the Moon. Charged particles from the solar wind get trapped in that field and spiral inward along magnetic field lines, funneling toward the poles like water down a drain. When they hit the upper atmosphere, they ionize hydrogen and methane, which glow in the ultraviolet and infrared. Webb caught both. But here's the part no one expected. The auroras don't just glow. They heat the atmosphere beneath them, pumping thermal energy into the stratosphere and raising temperatures by hundreds of degrees. That heat should radiate away into space within hours, but it doesn't. It spreads, carried by winds we can't yet map, and it shows up in Webb's thermal scans as a hot halo around both poles. The energy budget doesn't close. These weren't gentle curtains of light. They were engines pouring heat into the planet in a way no one could fully account for. Curtains of light. The auroras themselves are painted by charged particles, electrons and ions, that spiral down magnetic field lines and slam into the thin upper atmosphere at 111,000 miles per hour. Where they hit, hydrogen molecules glow. The collision strips electrons, releases photons, and the atmosphere burns in ultraviolet and infrared. Webb caught both. The rings aren't solid. They pulse, flicker, shift position by thousands of miles in minutes. The magnetic field lines that guide the particles wobble as Jupiter rotates, dragging the auroral ovals with them. Every 10 hours, the whole structure sweeps around the planet like a lighthouse beam. The particles arrive in bursts, not steady streams. Something upstream is accelerating them to enormous energy, then dumping them into the poles in waves. Ground observatories had measured this before, but Webb's infrared view showed the heat signature in real time, frame by frame. The curtains flared, cooled, flared again. For decades, the assumption was solar wind, the stream of particles blowing off the sun, compressed and funneled by Jupiter's magnetosphere. But the timing didn't match. The brightest auroras appeared when solar activity was low. And the source of that particle storm wasn't the sun, but something erupting from one of Jupiter's own moons. The Io connection. Io is the most volcanically active body in the solar system. It orbits Jupiter every 42 hours, locked in a gravitational tug-of-war with Europa and Ganymede that kneads its interior like dough. The friction melts rock. Sulfur dioxide geysers erupt 250 miles into space, freezing instantly and falling back as snow. But not all of it falls back. Io's gravity is weak, just 18% of Earth's, and the plumes are fast. A fraction of the gas escapes, ionized by sunlight and Jupiter's radiation. Every second, Io vents roughly 2,200 pounds of material into space. Most of it is sulfur and oxygen, stripped of electrons and electrically charged. Jupiter's magnetic field sweeps past Io at 128,000 miles per hour, scooping up those ions and dragging them along. The Moon becomes a source, a geyser feeding the magnetosphere. Voyager 1 discovered this in 1979. Galileo mapped it in the 1990s. But Webb's images revealed the scale of the exchange, the glowing footprint where Io's plasma funnel connects directly to Jupiter's aurora.
The connection is a flux tube, a pipeline of magnetic field threading between Moon and planet, carrying 3 million amps of current. It lights up both ends. That volcanic exhaust doesn't just drift away. It wraps the planet in a ring of electrified gas.
The plasma torus. The plasma torus is a donut of ionized sulfur and oxygen orbiting Jupiter at Io's distance, roughly 262,000 miles out. It's invisible in optical light, but glows in ultraviolet and radio. The density peaks near Io's orbit, then spreads inward and outward, held in place by the rotating magnetic field.
The torus contains roughly 200 pounds of new material every second, the same rate Io supplies it. But it doesn't grow. The plasma either escapes, blown outward by pressure, or it gets funneled down the magnetic field lines into the poles. That inflow powers the auroras. The particles accelerate, crash into the atmosphere, release their energy as light and heat.
Webb measured the temperature of the torus at 180,000 degrees Fahrenheit, hot enough to ionize sulfur multiple times over. The energy required to sustain that temperature, plus the auroral output, plus the heat radiating from Jupiter's upper atmosphere, adds up to more than 100 trillion watts. Models predicted maybe half that.
The discrepancy wasn't small, and it wasn't new. Astronomers had known since the 1990s that Jupiter's auroral system was too energetic. But Webb's infrared precision made the gap undeniable. Something was accelerating those particles beyond what the standard dynamo model allowed. But energy has to go somewhere, and where Jupiter's energy was going became the question that would haunt the rest of this story.
Rings revealed. Webb turned its gaze wider and caught something most ground telescopes had never clearly seen. Jupiter's rings, gossamer bands of dust stretching 225,000 kilometers from the planet's center, materialized in the infrared like smoke against black velvet. They're not ice like Saturn's. They're powder, micrometeorite debris, and fragments kicked up from tiny moons caught in Jupiter's pull, each grain scattering sunlight too faintly for visible light cameras to register. Voyager glimpsed them in 1979, but Webb's sensors made them sharp, tracing the main ring at 122,500 kilometers radius and the gossamer extensions beyond.
The structure wasn't uniform. Clumps and gaps hinted at orbital resonances, invisible traffic patterns carved by gravity. Faint as they were, those rings weren't alone in the frame.
Faint halos. Faint halos. Surrounding the rings was a diffuse halo, a cloud of the finest dust grains spiraling inward under magnetic drag and radiation pressure. Particles that small don't orbit cleanly. They drift, ionize, get swept into the magnetosphere, or pulled toward the planet, creating a gauzy veil that extends tens of thousands of kilometers in every direction. Webb's infrared band at 2.12 microns caught the thermal glow of that dust, mapping the density gradients no visible light image had ever resolved. The halo wasn't static. It pulsed with the planet's rotation, thickening where the magnetic field funneled particles inward, thinning where solar wind pushed them out.
That structure told a story of collisions, of moon shedding material grain by grain, of a system constantly grinding itself down. Tucked against that glow were two of the hardest moons in the solar system to ever photograph.
Hidden moons, Amalthea and Adrastea, shepherd moons smaller than most cities, appeared as faint points embedded in the ring plane. Amalthea spans just 250 kilometers at its longest axis, a potato-shaped chunk of ice and rock sitting 181,400 kilometers from Jupiter's center. Adrastea is tinier still, 20 kilometers across, orbiting at 129,000 kilometers and completing a lap every 7 hours.
Both are thought to source the ring material, chipped away by impacts too small to see, but constant enough to replenish the dust. Hubble had caught Amalthea before, but Adrastea remained a blur, lost in Jupiter's glare. Webb's contrast and wavelength choice cut through that glare, isolating the Moon's reflected infrared signatures against the planet's brightness. These weren't glamorous discoveries, but they mattered. Seeing them at all proved Webb could catch the faintest signals, which is exactly why what it caught next couldn't be dismissed as noise. The deeper puzzle. Webb's infrared eyes were built for exactly this kind of hunt. Jupiter radiates more energy than it receives from the Sun, and that imbalance has been measured since the 1970s. Voyager, Galileo, Cassini, they all confirmed it. The planet glows with internal heat, leftover warmth from its formation 4.6 billion years ago, slowly leaking into space.
But there's a second layer to the mystery, one that doesn't fit the slow cooling model. Jupiter's upper atmosphere, high above the clouds, sits at temperatures near 900 degrees Fahrenheit. That's hotter than boiling water. The Sun's radiation at Jupiter's distance should heat those layers to maybe 100 degrees Fahrenheit, not 900. Something else is delivering energy up there, and no one has caught it in the act. Ground telescopes couldn't resolve the structure. Hubble's instruments weren't sensitive enough in the right wavelengths. Juno orbits too close to see the global picture. Webb was the first tool capable of mapping Jupiter's thermal signature in enough detail to trace where the excess heat concentrates, how it moves, and what might be feeding it. For 50 years, one number about Jupiter simply didn't add up, and Webb was about to make that impossible to ignore.
The energy crisis. Planetary scientists call it the energy crisis. Jupiter's thermosphere, the outermost atmospheric shell before space begins, measures between 700 and 1000 degrees Fahrenheit, depending on latitude. Models driven solely by solar heating predict 73 degrees Fahrenheit. That's not a rounding error. It's a gap of 800 degrees persisting across the entire planet, day and night, pole to equator. Early theories pointed to auroras. Charged particles from the solar wind slam into Jupiter's magnetic field, spiral down toward the poles, and dump energy into the upper air. That works near the poles, where the auroras blaze. But the heat spreads everywhere, even to the equator where no aurora reaches. Auroral heating alone can't cross 90 degrees of latitude and maintain those temperatures.
Other candidates included atmospheric waves, chemical reactions in the ionosphere, even tidal forces from Jupiter's moons flexing the atmosphere like a gravitational bellows. Each mechanism contributes something. None of them, individually or combined, closed the 800-degree shortfall. The Sun delivers only a fraction of the heat needed, so something else has been secretly warming the planet for as long as we've watched it. Too hot to explain, Webb's July 2022 observations captured Jupiter's thermal emission in unprecedented detail. The data revealed temperature peaks not where models expected them. Mid-latitudes glowed hotter than the equator. Certain longitudes showed persistent warm spots that rotated with the planet's magnetic field, not its atmosphere. The heat wasn't evenly distributed. It was structured, organized. The thermosphere's baseline sits near 800 degrees Fahrenheit, but localized regions spiked to 1,100 degrees Fahrenheit. Those hotspots appeared directly above the planet's auroral ovals, then extended in narrow lanes toward lower latitudes. The pattern suggested a transport mechanism, something physical carrying energy away from the poles. Not diffusion, not convection, but a directed flow, invisible in visible light, but unmistakable in infrared. Scientists knew Jupiter's magnetic field rotates every 10 hours, dragging ionized gas with it. They knew plasma currents flow along magnetic field lines. What they didn't know was whether those currents delivered enough energy to account for the missing heat. Webb's maps gave them the first clear view of where the warmest air sits relative to the magnetic geometry. The correlation was tight, almost perfect. To find the culprit, scientists had to trace the heat backward, layer by layer.
Where heat comes from? When air sits hotter than it has any right to be, physicists start listing suspects. The first is auroral heating, energy dumped into the upper atmosphere by charged particles funneling down the magnetic field. The second is gravity waves, ripples that climb up from the churning weather below and break like surf against the thin air overhead, spilling their energy as they go.
The third possibility is stranger, that Jupiter carries some internal engine still bleeding warmth outward from its formation, 4.5 billion years on. Each theory predicts a different fingerprint in temperature and altitude, and for decades, no instrument could read those fingerprints cleanly. Webb changed that. Its measurements pointed toward a pathway most models had treated as a minor detail, an energy route no one expected to matter this much. The obvious suspect was the aurora, but the numbers there had never quite closed the gap.
The Sun's failure. Start with the Sun, because it's the easy answer and the wrong one. Jupiter orbits at roughly 5 times Earth's distance, so the sunlight reaching it is diluted to about 4% of what warms our sky. That trickle is thin fuel for heating anything, let alone the tenuous gas hundreds of kilometers above the clouds.
And there's a geometry problem. Solar heating should peak at the equator, where the light strikes most directly, then fade toward the poles. But the upper atmosphere runs hot across huge stretches of the planet, including latitudes the weak sunlight barely touches.
You can stretch the numbers, invent efficiencies, assume the air traps heat better than it should. It still doesn't add up. If the sun couldn't do it, and the aurora couldn't do it alone, the heat had to be coming from somewhere no one had mapped. Following the heat. So the search turned vertical. Webb doesn't just take a picture, it slices light into spectra, and each molecule glows at wavelengths that betray its temperature and altitude. By reading those signatures, the team could build a temperature profile stacked layer by layer, from the deep cloud decks up into the thinning haze at the top. They tracked where certain gases thickened, where they thinned, and where the warmth spiked out of step with everything around it. The goal was simple to state and brutal to execute. Follow the heat upward and find the altitude where the missing energy was hiding. Chunk by chunk, the maps filled in, and the numbers began to point at a specific place in the sky above Jupiter's storms. As the maps sharpened, a bright band of haze appeared exactly where the models predicted only darkness.
The bright haze. The haze wasn't faint. At wavelengths where Jupiter's upper atmosphere should have been nearly transparent, Webb's infrared cameras recorded a glowing layer stretching across the equator and wrapping over both poles. The signal was strong enough that early reviewers flagged it as a calibration error. But the haze was real. It sat roughly 300 kilometers above the ammonia cloud deck, in a region where pressure drops below 1 millibar and temperatures fall to 160 K. Models predicted thin, cold air at that altitude, too sparse to scatter much light.
Instead, Webb found a dense aerosol layer radiating in the 3 to 5 micron bands. The spectrum didn't match water ice, ammonia crystals, or any of the expected condensates. Whatever particles hung there were small, roughly 0.1 to 0.5 microns across, and abundant enough to blanket tens of thousands of square kilometers.
The brightness varied by latitude. Over the equator, the haze formed a continuous band. Near the poles, it broke into patchy arcs that flickered between observation passes. But haze doesn't glow on its own. Something had to be stirring it.
Dark patches. Between the bright bands, Webb recorded gaps. Dark patches appeared at mid-latitudes in both hemispheres. Oval voids, where the infrared signal dropped by 40% or more. They weren't storms. The Great Red Spot and smaller anticyclones showed up clearly in visible light, but left no dark signature in the thermal channels.
These features were colder than their surroundings, sometimes by 15 K. That temperature difference suggested either a clearing in the haze layer, exposing the frigid stratosphere below, or a region where downwelling air compressed and warmed just enough to evaporate the aerosols.
The distribution was irregular. Some dark ovals clustered near 30 degrees latitude in tight chains. Others appeared isolated, drifting across featureless zones with no visible anchors in the cloud decks beneath them. A few stretched into elongated filaments, as if pulled by shear. Observers mapped 23 distinct dark features in the first mosaic. When Webb returned 11 hours later for a second pass, 19 remained. But their positions had changed. 4 had vanished entirely, and 3 new patches had opened at longitudes that had been bright before. Some of those dark patches shifted between images, as if being dragged by an invisible current.
Ghost features. The transient features didn't behave like clouds. Ammonia plumes rise, spread, and dissipate over days as convection cells churn the troposphere. These structures appeared and disappeared within hours, sometimes between consecutive orbits. Their lifetimes ranged from 3 to 9 hours, far too short for any condensation cycle.
Webb captured one feature forming in real time. At 1422 UTC, a faint arc began to brighten at 42 degrees north, growing from a thin crescent into a comma-shaped glow over the next 87 minutes. By 1650 UTC, it had faded back to background levels. The sequence covered just 2.5 hours, but the structure travelled 4,200 kilometres eastward during that window.
That speed, 470 meters per second, exceeded the zonal wind velocity at every measured altitude. The fastest jet streams on Jupiter peak near 180 meters per second in the cloud tops. No known atmospheric flow at that latitude could push material faster than 200 meters per second, yet these ghost features raced by at more than twice that rate. Other transients moved westward against the prevailing wind, or drifted poleward across stable latitude bands. Their trajectories didn't follow the cloud belts or match any circulation pattern in the existing wind maps. Whatever was moving them was fast, high, and completely absent from every atmospheric model of Jupiter.
Chasing shadows. The team turned to frame-by-frame tracking. They marked each feature, measured its position against Jupiter's coordinate grid, then watched it move across the next image. Small features drifted a few pixels. Bright spots traced arcs. Dark filaments stretched and twisted as the planet rotated beneath them.
Every displacement became a velocity. Every velocity pointed to wind speed at that altitude. The work was slow. A single feature might appear in 12 frames over 10 hours, giving 11 measurements of motion. Multiply that by hundreds of features across dozens of latitudes, and the full wind map took months to assemble.
Some features vanished after a few rotations. Others lingered for weeks, stable enough to track across multiple observation runs. The longest-lived targets gave the cleanest data. The team catalogued them, built spreadsheets of coordinates and timestamps, then fed the numbers into circulation models to see where the atmosphere was actually moving.
The speeds they eventually measured would rewrite the textbooks. Before they could measure the high winds, though, they had to understand the storms churning far below. Storm machines. Jupiter's weather starts deep. Ammonia vapor rises from the hot interior, cooling as it climbs until it condenses into clouds. The condensation releases heat, warming the surrounding gas and driving it upward even faster. That's convection, the same engine that builds thunderstorms on Earth, but amplified by gravity 2.5 times stronger and a hydrogen atmosphere 11 times wider.
The result is storm systems larger than continents. Some are cyclones spinning for decades. Others are convective towers, rising plumes of ammonia and water ice that punch through cloud decks at hundreds of meters per second. The Great Red Spot is a storm 16,000 kilometers wide, sustained by energy drawn from layers hundreds of kilometers down.
These storms don't just move horizontally, they churn the atmosphere vertically, mixing material between pressure levels that would otherwise remain stratified. Juno's microwave radiometer had already shown that the biggest storms reach at least 350 kilometers below the visible cloud tops, their routes anchored in regions where the pressure exceeds 100 bars and the temperature climbs past 400 K. JWST's infrared eyes caught the upper signatures of that churning, bright convective plumes breaking through the ammonia deck, turbulent wakes trailing behind rising towers, dark zones where descending air compressed and warmed. And these storms weren't shallow weather, they had roots plunging thousands of kilometers down.
Lightning below. Lightning confirmed it. Juno had detected powerful electrical discharges in Jupiter's clouds, some releasing energy equivalent to terrestrial superbolts, the rarest and most violent lightning on Earth. The flashes came from the water cloud layer, roughly 80 kilometers below the visible ammonia deck, where droplets collide and charge separation builds until the atmosphere breaks down.
Each discharge marked a convective cell strong enough to lift water vapor from depths where the temperature exceeds the boiling point of water at Earth sea level. The storms weren't just mixing ammonia, they were dredging material from the warm, wet interior and hurling it upward through 5 or 6 distinct cloud layers, each with different chemistry, different particle sizes, different optical properties.
JWST couldn't see the lightning directly, but it saw the aftermath. Bright patches appeared hours after Juno recorded discharge clusters at the same longitude. The patches glowed in mid-infrared, warmer than their surroundings, as if the convection had pushed heat upward and left it pooled in the upper troposphere. The storms were acting as pipelines, connecting the deep, hot interior to the cold cloud tops.
And the deeper the roots, the more energy they could carry. Models suggested the largest convective systems might reach 3,000 kilometers down, into regions where hydrogen begins to behave less like a gas and more like a supercritical fluid. Each flash hinted that energy from the depths might be climbing toward the layers that were too hot to explain. The deep weather. Webb's infrared sensors could peer through the high ammonia haze, but they still hit a wall around 100 kilometers below the visible deck. Cassini's microwave instrument had gone deeper during its Jupiter flyby in 2000, mapping pressure levels down to 10 bars, nearly 200 kilometers beneath the tops of the clouds. What it found wasn't a uniform interior. Temperature and composition swung wildly between latitude bands.
The Great Red Spot's roots extended at least 500 kilometers down, confirmed by Juno's gravity measurements in 2017. Smaller oval storms reached 200 to 300 kilometers, but the convective plumes feeding them, the chimneys of rising heat, could tunnel much deeper. Radio occultation data from Voyager suggested density shifts near the 1,000 kilometers mark, where pressures exceed 2,000 Earth atmospheres. At those depths, hydrogen stops behaving like the gas we know. It becomes a supercritical fluid, neither liquid nor gas, and its ability to transport heat changes. If convection cells punch through that transition, they'd mix energy from Jupiter's metallic core region with the weather we see at the top. The clouds themselves were carrying a chemical fingerprint of that hidden circulation.
Ammonia clouds. The brightest clouds in Webb's images glowed in wavelengths absorbed by ammonia ice, confirming what Galileo's probe measured in 1995. That layer sits around the 0.7 bar pressure level, roughly 50 kilometers below the haze. Ammonia condenses there because temperatures drop to around 150 K. Below it, around 2 bars and 200 K, ammonium hydrosulfide forms, a dirtier ice made of ammonia reacting with hydrogen sulfide rising from deeper layers.
Webb caught both. The ammonia clouds showed up as bright white in near-infrared filters at 2.12 microns. The ammonium hydrosulfide layer appeared as a darker orange-brown at 3.23 microns, exactly matching lab spectra from the 1980s. Where storms punched through, fresh ammonia surged upward, freezing into new crystals that scattered light and appeared as brilliant plumes. The Great Red Spot's core showed ammonia concentrations 3 times higher than surrounding bands.
But the pattern didn't match predictions. Equatorial zones should have been ammonia-rich, pulling material up from below. Instead, some showed depletion, as if something was scrubbing ammonia out, or locking it into compounds mid-atmosphere. Models needed a third ingredient to explain the chemistry, something mixing in from even deeper. Beneath the ammonia lay a layer no telescope can see directly, and it may hold the key to everything.
Water question. Water. On Earth, it's 0.04% of the atmosphere. On Jupiter, no one knows. The Galileo probe descended into an unusually dry region in 1995 and measured just 0.1% water vapour before it was crushed at 22 bars. Juno's microwave radiometer found huge variations, from bone-dry zones at the equator to water-rich plumes near 50 degrees north, some carrying 5 times the solar abundance. That's more oxygen than the planet should have if it formed where it did.
Water clouds should condense around 5 bars, roughly 100 kilometers below the ammonia deck, where temperatures hit 273 K. If they exist, they'd anchor the deepest convection cells, releasing latent heat as vapor freezes and driving storms upward. Webb's spectroscopy picked up water absorption lines at 2.9 microns in some storm updrafts, confirming trace amounts reached the upper troposphere. But the bulk reservoir stayed hidden. The mystery matters because water controls energy. If Jupiter is water-rich deep down, convection would be more violent, storms bigger, and heat transport faster. If it's dry, the extra warmth has to come from somewhere else. The models couldn't balance without knowing. Every measurement pointed to a deep, uneven ocean of water vapor, mixed unevenly by circulation we still don't fully map. Water or not, the real drama was unfolding far above the clouds, in a layer almost no one had thought to watch.
Layers unseen. Jupiter's atmosphere isn't one layer, it's a stack. At the bottom, 1,000 kilometers down, pressures crush hydrogen into liquid metal. Above that, molecular hydrogen clouds billow in zones and belts, churning ammonia ice and ammonium hydrosulfide crystals into the storms we've watched for centuries. Higher still, the air thins. The troposphere gives way to a boundary where convection fades and temperatures stop falling with altitude. This tropopause sits roughly 50 kilometers above the cloud tops, marking the edge of Jupiter's weather layer. Everything below is turbulence and heat rising from the interior.
Above the tropopause, the stratosphere begins. The air here is so thin that pressure drops to millibars, then microbars. Methane and acetylene haze float in this cold shell, absorbing faint ultraviolet from the sun. For decades, telescopes saw only the bright clouds below. The stratosphere was too faint, too high altitude to map in detail. Webb changed that. Its infrared sensors locked onto thermal emissions from the upper layers, isolating stratospheric signatures that Hubble and ground telescopes couldn't separate from the noise below. At the very top, in the thin, cold stratosphere, Webb saw something no instrument had ever resolved. The stratosphere. The stratosphere was supposed to be Jupiter's calm zone. No convection, no rising plumes, no storms. Heat from the interior doesn't reach this high. The only energy input is solar radiation, weak at 5.2 AU, barely warming the methane haze to 110 K.
Models predicted slow, stable circulation. Winds at these altitudes were thought to drift at maybe 50 or 60 meters per second, driven gently by solar heating differences between equator and poles. Voyager couldn't measure them. Galileo's probe never reached this layer. Cassini glimpsed motion but lacked the resolution to map velocities. Juno measured gravity and magnetic fields but couldn't track individual wind speeds in the stratosphere. Ground-based infrared campaigns saw temperature patterns that hinted at movement, but turning temperature maps into velocity required assumptions the data couldn't validate. The upper atmosphere remained a sketch, not a measurement.
Webb's NIR spec instrument changed the equation. By tracking small-scale thermal features frame by frame across multiple observation windows in 2022 and 2023, the team could calculate wind velocities directly from feature displacement. This layer was supposed to be gentle, but the numbers coming back were anything but gentle.
Winds above. The first hint came from equatorial temperature anomalies. Small bright patches in the stratosphere, only a few hundred kilometres across, moved eastward faster than any model allowed. The team ran the displacement calculations twice, checking for instrument drift or processing errors. The features were real and they were racing. At 30 Vedel M-bar pressure, roughly 200 kilometres above the ammonia cloud deck, wind screamed along the equator at velocities that dwarfed the tropospheric jets below. The troposphere's equatorial jet tops out near 100 metres per second. The stratospheric flow was multiples of that. Not double, not triple.
The data showed no plausible energy source. Solar heating at Jupiter's distance couldn't drive winds this fast in such thin air. The interior heat didn't reach this high. Gravity waves from storms below could carry momentum upward, but the amplitudes required would tear the lower atmosphere apart. Something was accelerating gas to extraordinary speeds in a layer that shouldn't even have weather.
The principal investigator ran the numbers through 3 independent pipelines before releasing them. Each confirmed the same result. When they finally measured the speed, no one believed it on the first pass.
Measuring motion. The technique itself was elegant. Webb locked onto small bright features in Jupiter's upper haze, clouds of ammonia ice suspended 25 miles above the deeper weather. Engineers tracked them frame by frame across a 10-hour rotation, measuring how far each feature traveled against Jupiter's known spin rate. The difference between the planet's rotation and the haze motion gave the wind speed, but this only worked because Webb's infrared eyes could isolate a specific altitude, a narrow band in the stratosphere where Hubble saw nothing but blur. 3 separate wavelengths cross-checked the altitude, all 3 locked onto the same layer. The team processed 7 hours of continuous imagery, mapping 43 distinct haze features as they drifted eastward. Every feature moved in sync, a coordinated flow at one precise height. When the velocity came back, the lead scientist triple-checked the calibration files. The result described a river of wind hidden in plain sight, wider than Earth and faster than any storm below.
The hidden river. They called it a jet stream, but that phrase doesn't capture the scale. On Earth, jet streams are ribbons of fast air 5 to 9 miles up, steering weather systems across continents. Jupiter's version sits in the stratosphere, a realm scientists thought was too thin and too calm to sustain organized flow. The discovery sat in draft form for 6 weeks, while the team hunted for errors. They reprocessed the data with different noise filters. They cross-referenced archive images from ground telescopes to confirm the haze layer was stable enough to track. Every test returned the same answer: a coherent wind structure occupying a band 1/900 miles wide, circling the equator in a perfectly straight line.
No model had predicted it. No previous mission had the resolution to see it. The jet existed in a gap between what Voyager could measure below and what ground telescopes could resolve above. Webb split that gap open. This was the thing that had stopped the room cold months earlier, and now it finally had a shape. The jet appears. The jet runs like a highway painted across Jupiter's equator, narrow and relentless. It sits 25 miles above the cloud tops, in a zone where atmospheric pressure drops to 1 millibar, thinner than the air at Earth's highest mountain peaks. The haze particles caught in this current are ice crystals smaller than smoke, drifting in near vacuum compared to the thick ammonia storms below. What stunned the team was the jet's coherence. Earth's stratospheric winds meander, split, and reform. Jupiter's version holds a laser-straight path, no wobble, no eddies, no breaks for thousands of miles. It doesn't interact with the storms beneath it. The Great Red Spot spins 400 miles below, and the jet above ignores it completely. The discovery rewrote the map of Jupiter's atmosphere in a single image. For 40 years, scientists believed the equator was a battleground of opposing winds, east and west currents grinding against each other in the deeper clouds. Webb revealed a third player, operating in isolation at altitude, untouched by the chaos below. Then they attached a number to it, and Jupiter's textbooks started to look obsolete.
faster than storms. The jet was moving at 320 metres per second. That's roughly 715 miles per hour, sustained, in a narrow channel 3,000 kilometres above the cloud decks we've mapped for centuries.
For context, the fastest hurricane winds ever recorded on Earth topped out around 190 miles per hour for brief moments during Patricia in 2015. This jet was running at more than twice that speed, continuously, across tens of thousands of kilometers. The Great Red Spot, Jupiter's most famous storm, churns at around 400 miles per hour at its edge. The equatorial jet above it was outpacing even that, in a layer so thin and so high that no spacecraft had ever directly measured winds there before.
Speed alone wasn't the shock. It was where this river of air was flowing that broke the rules.
The equator line. The jet sits precisely over Jupiter's equator, threading through the stratosphere roughly 40 kilometers above the ammonia ice clouds that define the planet's visible face. It's locked in place, stable, a narrow band of motion where the atmosphere should be calm. On Earth, stratospheric jets exist, but they're driven by seasonal heating, by the tilt of the planet, by temperature gradients that shift with the sun. Jupiter has almost no axial tilt, no seasons, and its internal heat should dominate over solar input at that altitude. The equator is also the one place on Jupiter where Coriolis forces vanish. There's no deflection to organize winds into coherent flows, no invisible hand to bundle air into jets the way it does at mid-latitudes. Nothing in the standard picture of Jupiter should be able to hold a jet like that in place.
A belt of speed. Webb's infrared data showed the jet stretching across roughly 4,800 kilometres in width, confined to a vertical layer no thicker than 40 kilometres. It threads through hazes that appear only in the near-infrared, traces of high-altitude chemistry invisible to Hubble and every Earth-based telescope before it.
The jet sits above the tropopause, the boundary where Jupiter's weather ends and its stratosphere begins. Below that line, convection drives everything: the belts, the zones, the storms, the churning cells that transport heat from the deep interior. Above it, the atmosphere should be stratified, stable, inert. Yet here was a feature moving faster than the storms below, isolated from the engine that powers them, confined to a layer where nothing should be moving at all. Every model of Jupiter's circulation had missed it, because every model assumed the stratosphere was irrelevant.
So the question everyone finally had to face was simple and impossible. What is powering this thing?
What drives it? The deep convection models pointed to energy rising from below, but the jet sat 40 kilometers above the weather layer, isolated by stable air that blocks vertical transport. Heat couldn't just leap that gap.
The auroral models traced energy cascading down from the poles, where Jupiter's magnetosphere dumps millions of watts into the upper atmosphere. But the equator lies thousands of kilometers from those glowing rings, and no mechanism connects polar heating to equatorial winds. Then there was the third option, the one no atmospheric model included. Jupiter's stratosphere itself might be holding trapped heat, radiating more energy than it absorbs from the sun. Haze layers, chemical reactions, waves propagating from below, all depositing energy exactly where the jet lived.
Each pathway had observational support. Each pathway had theoretical gaps wide enough to crash a spacecraft through. The candidates all pointed in one direction, and it was the last place anyone wanted the answer to be.
The great reveal. Webb's infrared data didn't just reveal the jet, it confirmed what Voyager had whispered 50 years earlier. Jupiter's stratosphere is radiating 14% more energy than the planet receives from the sun, and no one knows where that excess is coming from.
The jet's discovery made the energy crisis impossible to ignore, because here was a 320 kilometers per hour wind sitting in the exact layer where the mystery heat lives. The two anomalies occupied the same altitude, the same latitude band, the same thermal environment.
But matching the location didn't solve the mechanism. If auroral energy powers the jet, why does it appear at the equator and not the poles? If deep storms drive it, how does momentum cross the barrier layer? If stratospheric chemistry fuels it, where are the reaction signatures?
Webb handed planetary scientists a dataset connecting two unsolved problems with no clear path between them. The images were sharp, the measurements precise, the correlation undeniable. The explanation remained out of reach. Handing scientists a mystery this clean did something unexpected. It split the experts straight down the middle. Experts divided. One camp argued the jet proves auroral coupling works across distances no one predicted, that magnetic field lines and charged particles create highways between the poles and equator. They pointed to the jet's confinement in pressure zones where ionized molecules cluster, to timing correlations between auroral storms and stratospheric temperature spikes.
The opposing group insisted deep convection must be the driver, that gravity waves and acoustic pulses carry momentum upward through barriers models treat as impermeable. They cited the jet's alignment with equatorial hotspots in the lower atmosphere, the way its speed mirrors storm intensity thousands of kilometers below.
A smaller third faction suggested something new entirely, that Jupiter's stratosphere operates under physics Earth's atmosphere never taught us, where chemical networks and radiative transfer create circulation patterns with no terrestrial analog. The excess heat, the impossible jet, both symptoms of processes we lack the framework to model. Conference talks turned into debates. Papers cited the same Webb images to argue opposite conclusions. Each side had strong evidence, and each side had a hole in its argument big enough to fly a probe through.
The missing mechanism. The core problem is deceptively simple. Every atmospheric model we have says stratospheric winds this powerful require an energy source, and every energy budget for Jupiter's upper atmosphere comes up short by a factor of 3 or more. If you pump in heat from below, the way Earth's jet streams work, you solve the wind speed, but create temperatures 40 degrees hotter than Webb actually measured. If you cool the stratosphere to match observations, the winds collapse to half what we see.
Researchers tried hybrid models, tuning dozens of parameters across months of supercomputer time. The jet either disappeared, migrated 15 degrees off the equator, or required an influx of 8 terawatts with no identified source. One team at Caltech ran 147 simulations, and every single one failed at least one constraint.
To even attempt an answer, some researchers started reaching for physics that had never been applied to Jupiter. Beyond the models. The models being rewritten weren't speculative, they were workhorses. NASA's Goddard Institute used its Jupiter circulation model to plan Juno's orbit. ESA's team validated Galileo probe data against the same equations for 12 years.
Now entire sections of those codes were being flagged as incomplete. The radiative transfer solvers assumed stratospheric winds stayed below 140 meters per second, so they never coded in the turbulence regime that appears above that threshold. The chemistry modules treated the upper atmosphere as a passive layer, not an active player capable of generating its own circulation. At a workshop in Pasadena, a modeler from JPL put it bluntly, "We built these tools to explain what Voyager saw in 1979, and Webb just showed us a different planet. Revisions would take years, maybe a decade, and require data points Webb hadn't been designed to capture." One promising thread led straight back to those blazing poles we started with.
The auroral link. Jupiter's auroras dump roughly 10 terawatts into the atmosphere every second. Most of it concentrated above 60 degrees latitude. That's 100 times the energy of Earth's entire aurora system, delivered as high-speed charged particles, slamming into the upper layers and heating them to 730 degrees Celsius.
A handful of teams started asking whether some fraction of that auroral energy could leak equatorward, channeled by magnetic field lines, or carried by atmospheric waves we've never directly observed. If just 15% of the polar influx reached the equatorial stratosphere, the energy budget closes and the jet becomes possible. The idea is tantalizing because it ties two of Webb's most striking findings into one mechanism. The light show and the hidden wind wouldn't be separate mysteries, they'd be cause and effect, two faces of the same planetary engine. Early simulations from a group in Tokyo showed promise. Seed the model with auroral heating at 70 degrees north and south, wait 80 Jovian days, and a narrow equatorial jet begins to spin up. But moving heat from the poles to the equator on Jupiter is like a river running uphill, and no one can yet say how.
Feeding the winds. The auroral hypothesis needs something the models can't yet provide, a transfer pathway. Energy dumped into the thermosphere at 70 degrees latitude has to tunnel downward through 500 kilometers of stratosphere, then radiate equatorward through regions where temperature gradients say it shouldn't. Friction alone can't explain it. Gravity waves might carry momentum, but their amplitude falls off exponentially with depth. A second problem is timing. The jet spins at 430 AMRs, but the aurora flickers on timescales of hours. To sustain that kind of velocity for decades, the energy input would need to be continuous and precisely tuned. Webb's infrared sensor caught thermal signatures in the equatorial stratosphere that matched auroral pulses 9 hours earlier, hinting at a lag, but the resolution wasn't fine enough to trace the full cascade. Then there's the accounting. Jupiter radiates 1.67 times the energy it receives from the Sun. The difference, 5.4x 10 MeV 17 watts, comes from primordial heat still leaking out of the core. The jet by itself would require only a small fraction of that, maybe 10^4 15 watts. But when researchers at Caltech summed the known losses, absorption by methane bands, heat redistribution by eddies, and radiative cooling at cloud tops, the numbers didn't close. Every attempt to balance the energy ledger left the same stubborn surplus unexplained.
A new physics. There's a third option. Quieter than the others, but gaining traction in preprint archives. Maybe the equations are right and the observations are right, but the assumptions linking them are incomplete. Atmospheric physics on Earth rests on 200 years of lab work, weather balloons, and satellite data. Jupiter has none of that foundation. Its pressure at the cloud deck is 1 bar, comfortable and familiar, but 100 kilometers down it hits 10 bars, then 1,000. Then, a transition zone where hydrogen stops behaving like a gas. Textbook thermodynamics assume ideal gases and local thermodynamic equilibrium. Jupiter's interior violates both. Molecular hydrogen becomes metallic under pressure. Helium rain condenses out and falls toward the core, releasing gravitational potential energy as it descends. Magnetic fields threading the metallic layer can store and release energy in ways that don't appear in standard circulation models. The jet might be siphoning power from processes we've never seen in a laboratory.
If that's true, then Jupiter isn't an outlier. It's a test case, the clearest example of atmospheric behavior that our current frameworks can describe but not predict. A handful of researchers are revisiting Navier-Stokes under non-ideal conditions, tweaking the viscosity terms, adding magneto-hydrodynamic coupling. The math gets ugly fast, and solutions are sparse. If Jupiter really is breaking the rules, then its cousins should be breaking them too. Comparing worlds, Saturn's equator shows a jet clocked at 400 MeV, nearly as fast as Jupiter's, but Saturn receives only 1% of the sunlight and radiates 1.78 times what it absorbs. Its upper atmosphere is 30 degrees warmer than models predict. Cassini's final plunge in 2017 recorded unexpected turbulence in the thermosphere, suggesting energy injection from below or from the magnetosphere. The mechanism remains unconfirmed, but the signature is there.
Uranus and Neptune are stranger still. Both are ice giants with thin hydrogen envelopes, and both radiate more heat than they should. Neptune, 30 times farther from the Sun than Earth, has the fastest winds in the solar system, 600 meters per second in a narrow southern jet. Its atmosphere is colder than Uranus, despite being farther out, and its internal heat flux is 2.6 times solar input. Voyager 2 glimpsed auroral arcs in 1989. Ground-based infrared campaigns in 2022 found warm spots at 60 degrees south that flared and faded on 4-hour cycles.
Uranus shows the opposite behavior. It radiates almost exactly what it receives, as if its internal furnace went out. But Keck Observatory detected methane emission spikes in 2014 and 2021 near the equator, implying transient heating events with no obvious driver. 4 planets, 4 different heat budgets, but the same recurring anomaly. Equatorial jets that shouldn't exist, and upper atmospheres that glow without a clear cause. A pattern across 4 giant worlds would mean this isn't a Jupiter quirk at all, but something we've fundamentally misunderstood about planets. What it means. If our atmospheric models can't predict what's happening at Jupiter, they can't be trusted for the thousands of exoplanets we're cataloguing light years away. We use Jupiter as the template. Hot Jupiters, cold Jupiters, super-Earths with thick hydrogen envelopes. They're all modelled on assumptions built here in our own backyard. Webb found equatorial winds at 400 meters per second when theory said they'd stall at 100. It found stratospheric glows with no matching energy input. Those aren't minor discrepancies you smooth over with a software patch. They're foundational cracks.
Astronomers are already walking back confidence intervals on exoplanet wind maps and thermal profiles. A Nature Astronomy paper in July 2023 recalculated HD 189733b's atmospheric circulation after Jupiter's Webb data came in, downgrading certainty from 92% to 68%. One recalibration among hundreds that will follow.
And if we can't fully read a planet in our own solar system, it raises hard questions about the distant worlds we claim to understand.
The storms remembered. The Great Red Spot has been shrinking for 150 years. Voyager measured it at 23,000 kilometers across in 1979. Hubble clocked it at 16,000 kilometers in 2014. Webb's 2022 infrared frames show 14,000 kilometers, still contracting, still spinning, still defying every longevity model we've written. Oval BA appeared in 2000 when 3 smaller storms merged. It turned red in 2006, faded to white in 2008, then vanished entirely by 2020. No one predicted the merger. No one explained the color shift. No one knows where the energy went when it dissolved. Webb caught a newborn cyclone at 37 degrees north in August 2022, winds clocking 180 meters per second, temperature core 12 degrees warmer than surroundings. 6 weeks later, it was gone. The dataset recorded birth and death, but the physics that governed both remain out of reach.
Piece by piece, Webb wasn't just adding facts about Jupiter, it was rewriting the planet from the top down.
Rewriting Jupiter. Jupiter was the first planet Galileo turned his telescope toward in 1610. He saw 4 moons and proved not everything orbited Earth. Pioneer 10 flew past in 1973 and measured a magnetosphere 100 times stronger than predicted. Galileo Orbiter arrived in 1995 and found an ocean beneath Europa's ice snow model had anticipated. Every generation thought they'd finally pinned Jupiter down. Then Webb spent 8 months staring at it in 2022 and 2023, and the list of unexplained phenomena doubled. The polar hexagons, the equatorial jet, the stratospheric brightenings with no heat source, the storm cycles that ignore our equations. A 2023 review in Space Science Reviews tallied 17 major Jupiter assumptions overturned or under review since Webb's first full observation season. Not small corrections, paradigm-level shifts in how energy moves, how storms form, how a gas giant sustains itself over billions of years.
The rewrite is far from finished because Webb is still watching and Jupiter keeps changing. Watching and waiting. Webb's near-infrared camera returns to Jupiter every 68 days now, part of a cycle coordinated with ground telescopes in Hawaii and Chile. Each pass captures the equatorial jet in 4 wavelengths, tracking temperature shifts down to 0.3 degrees Kelvin. The heat plume Goddard flagged in August 2022 has moved 11 degrees west and cooled by 18 K, but a second hot zone appeared 22 degrees behind it in March 2023. Lee Fletcher's team at Leicester cross-references every new image with Juno's magnetometer sweeps, searching for correlations between magnetic flux and thermal spikes. So far, they've logged 6 candidate events where a field line reconnection precedes a temperature jump by 40 to 90 hours. The statistical confidence sits at 2.8 sigma, not enough to publish, but enough to keep watching.
Hubble joins the effort too, monitoring the ultraviolet auroral oval every time Webb images the mid-latitudes. The goal is a time series dense enough to catch energy transfer in the act, frame by frame, wavelength by wavelength. It's patient work, the kind that takes years to pay off. But every answer Webb returns seems to open 2 more questions in its place.
Questions multiply. If auroral energy does feed the equatorial jet, why doesn't Saturn show the same signature? Cassini mapped Saturn's pole-to-equator winds in exhaustive detail and found no comparable heat excess at mid-latitudes. The magnetic geometry is different, sure, but both planets share hydrogen atmospheres, fast rotation, strong fields. The divergence suggests a threshold or trigger we haven't identified yet.
Then there's chemistry. Webb's spectroscopy reveals ammonia ice crystals forming and sublimating in the jet's shear layers at rates 30% faster than models predicted. That phase change cycle releases latent heat, potentially feeding back into the very turbulence that lifts the crystals in the first place. Imke de Patter's group is now questioning whether chemical heating might rival magnetic input, a variable no pre-Webb simulation even included.
And timing remains the sharpest thorn. Jupiter's atmospheric features evolve on overlapping scales. Cloud bands shift over months. Storms merge over weeks. Temperature anomalies flicker over days. Webb's 68-day cadence catches snapshots, not the continuous flow needed to untangle cause from effect. The gaps between observations could be hiding the exact moments when energy couples from one layer to the next. Step back far enough, and Jupiter's puzzle becomes a mirror for something much larger than one planet.
The bigger picture. Every gas giant we've studied defies our atmospheric models in a different way. Uranus radiates almost no internal heat, despite forming the same way Jupiter did. Neptune's winds scream at 2,100 kilometers per hour, with barely any solar input to drive them. Hot Jupiters orbiting other stars show temperature inversions we can't reproduce in lab simulations. The common thread isn't that we're slightly off. It's that we're missing foundational physics that governs how energy moves through thick, rotating atmospheres under extreme conditions. Jupiter's heat anomaly is one data point in a much broader crisis of understanding. We've built climate models for Earth, Mars, Venus, and Titan, and every single one required post hoc corrections after spacecraft returned real measurements. The equations we use for fluid dynamics, radiative transfer, and thermodynamic equilibrium work beautifully in controlled environments. They fracture when applied to planets, where thousands of interacting processes cascade across 12 orders of magnitude in scale. Webb didn't break Jupiter science because the telescope is flawed. It broke it because the telescope is good enough to see what's actually happening, and what's actually happening doesn't fit the century of theory we built while squinting through Earth's atmosphere. We're watching a 140,000 kilometers wide laboratory rewrite the rules in real time, and we don't yet have the language to describe what the experiment is teaching us. And that scale of not knowing forces a strangely intimate question about our own place beside this giant.
Us and the giant. We've built machines that can resolve storms the width of continents on a world 600,000 kilometres away. We've catalogued its moons, mapped its magnetic field, measured the composition of clouds we'll never touch. And yet the closer we look, the less Jupiter resembles the planet we thought we understood.
Every answer Webb delivers carries a dozen new questions. The jet that shouldn't exist but does. The heat that pours from depths we can't see into. The waves that propagate through hydrogen at pressures no lab can recreate. We're watching a system that obeys physics we haven't written down yet.
Maybe that's the point. Maybe studying Jupiter was never about mastering it, never about building a perfect model that predicts every swirl and temperature spike. Maybe it's about learning to sit with the discomfort of a universe that refuses to simplify itself for our convenience.
We send telescopes into the cold because the act of looking matters, even when, especially when, what we see doesn't make sense. Because a civilization that stops asking is a civilization that's decided it knows enough. And Jupiter, 318 times Earth's mass, spinning in the dark, is proof we don't. There is still one list nobody likes to read aloud. Everything about these images we still can't explain.
What remains hidden? Start with the jet itself. We know it's there at 650 kilometres per hour, circling the equator like a river with no bed. We don't know what drives it. The sunlight Webb measured isn't enough. The internal heat isn't distributed right. Something is feeding energy into that jet, and every model that tries to account for it breaks somewhere else in the atmosphere.
Then there's the heat surplus. Jupiter radiates 1.7 times the energy it receives from the Sun. The textbook answer is primordial heat from formation, gravitational contraction, helium rain settling through metallic hydrogen. But the numbers Webb returned don't match. The thermal maps show hot zones that shouldn't be hot, cold pockets where warmth should pool, gradients that imply convection cells we can't see, and circulation we can't model.
The auroral emissions keep spiking at frequencies that don't align with the magnetosphere's rotation. Something is injecting particles into the polar regions on a schedule we don't control and can't predict. The Great Red Spot is shrinking, yes, but it's also intensifying. Wind speeds inside have increased 8% since Voyager, even as the storm contracts. Physics says it should be dying. It's not.
And the hazes. Webb's infrared cut through them to reveal a stratosphere laced with compounds we didn't expect. Complex hydrocarbons, ammonia ices at altitudes they shouldn't survive, temperature inversions that flip every convection model on its head. Each anomaly is small. Together, they form a portrait of a planet operating under rules we haven't learned to read. Holding all of it together, one final thought refuses to let go.
The unanswered. Webb showed us a Jupiter we no longer recognize, not because the planet changed, but because the resolution finally caught up to the complexity that was always there. For 400 years, we've watched Jupiter through glass and math, building models from smeared light and pixelated storms. We convinced ourselves we understood.
Then a 6.5-meter mirror unfolded 1,500,000 kilometers from Earth, cooled to 40 K, and pointed 18 gold hexagons at a world we thought we'd already catalogued. The images it returned were sharper, colder, stranger. The jet that rewrites atmospheric physics, the heat that doesn't add up, the storms that refuse to die, the chemistry that shouldn't exist. This isn't a telescope malfunction. This is the difference between looking and seeing. Hubble gave us Jupiter in outline. Juno gave us close passes through the magnetosphere. Webb gave us the whole atmosphere at once, in wavelengths that don't lie, at a resolution that exposes every assumption we'd papered over with good enough models.
What we're seeing is a gas giant in full detail for the first time, and the detail is wrong. Wrong by the standards of a century of planetary science built on inadequate data. The models aren't broken because they were bad science. They're broken because they were built on blurry images of a system too complex to guess from a distance. Before we close the loop, there's one more layer to this story that changes how you'll see every image we've discussed. The next window. Webb's next Jupiter observation window opens in 2026. Scientists have already filed proposals to map the same infrared bands, targeting the exact coordinates where the phantom jet appeared and tracking whether the auroral hotspots have moved or intensified.
The plan is simple. Capture the same wavelengths at the same resolution, compare pixel by pixel, and see if the anomalies are stable features or transient events. If the heat signature in the stratosphere has shifted, it tells you the mechanism is dynamic. If it hasn't, the mystery deepens, because nothing should stay that bright for that long without an energy source.
Some teams want to time observations with ground-based radio measurements, hoping to catch magnetic field fluctuations at the moment Webb sees auroral flares spike. Others are lobbying for longer exposures in the mid-infrared to isolate chemical signatures in the upper atmosphere, testing whether methane or ammonia is breaking down in ways current photochemistry doesn't predict. The hope is that repeated observations will reveal a pattern, a cycle, something that turns confusion into data. But Jupiter has spent 400 years defying that hope. But there's one implication no one wanted to say out loud.
The fragile models. If Jupiter's atmosphere operates outside the boundaries of our general circulation models, then every gas giant we've studied, catalogued, or theorized about inherits the same uncertainty. Exoplanet atmospheres are modeled using Jupiter as the reference case. Hot Jupiters, sub-Neptunes, ice giants orbiting distant stars all get their predicted wind speeds, heat distributions, and cloud layers from equations tuned to match what we thought Jupiter was. Formation theories assume Jupiter assembled in a way that matches observed gas giant characteristics. If those characteristics are wrong, the timeline shifts. The NICE model, which explains the outer solar system's architecture by simulating Jupiter's early migration, depends on assumptions about its mass distribution and atmospheric drag. Change the drag, change the migration path, and suddenly the Kuiper belt structure becomes a coincidence instead of a prediction. Planetary science didn't treat Jupiter as an unsolved problem. It treated Jupiter as the solved problem, the anchor point for everything else. Textbooks don't hedge when they describe gas giant dynamics. Mission proposals don't budget for the possibility that baseline assumptions are wrong. And now Webb has handed us images that don't fit. Not images of a distant, poorly understood exoplanet, images of the planet we thought we knew best, which brings us back to the photographs themselves.
What we're seeing. Look at the poles again. The auroral ovals glow at wavelengths that shouldn't penetrate that deep into the atmosphere, driven by magnetic field lines that curve in ways the simulations didn't anticipate. The infrared doesn't show storms. It shows structure, tessellated and geometric, like convection cells or standing waves locked into a pattern no fluid dynamics textbook predicts for a rotating gas envelope. The equatorial jet sits there in the data, 200 miles per hour faster than models allow, carving through the stratosphere at altitudes where drag should have killed it centuries ago. The heat bloom in the mid-latitudes glows hotter than solar heating can explain, hotter than auroral input should reach, hotter than any internal mechanism we've proposed can sustain without radiating away in days.
These aren't measurement errors. They're not instrumental artifacts. They're not ambiguous blurs waiting for better resolution. They're sharp, repeated, multi-wavelength observations of a world that does not behave the way physics says it should. Every image Webb captures is a portrait of ignorance, a reminder that 400 years of telescopes pointed at the same object didn't bring us understanding. They brought us confidence we hadn't earned. Jupiter is still unknown, not partially mapped, not awaiting a few final details. Unknown in the way that matters, the way that forces you to question whether the models describe reality or just describe our expectations. We've been watching the giant for centuries. We just weren't seeing it. The real question: Webb gave us the sharpest infrared portrait of Jupiter ever made. Not just sharper images, but views through wavelengths that strip away the clouds and reveal the machinery underneath. What it showed was a planet that doesn't match the physics we thought governed it. A stratosphere glowing with heat that has no identified source. Winds at 400 kilometers per hour in layers where no known mechanism can sustain them. Storms that organize themselves in patterns our models can't reproduce. Every answer opened 3 new questions.
The real question isn't whether we'll solve Jupiter. We will eventually, with more observations and better instruments. The real question is whether the universe we thought we understood, the one our textbooks describe with such confidence, is the one we're actually living in.
Because if a planet we've studied for 400 years can still surprise us this completely, what else are we getting wrong? Subscribe if questions like that keep you up at night. The giant is still spinning. We're still watching.